Okay, let's look at a problem here and try to put some of this stuff together so that it makes sense. So this is a projectile motion problem. We've got an airplane and we've got a box that we're going to deliver to some folks on a mountainside or a peak. We've got an Alaskan rescue plane dropping a package of emergency rations to some stranded hikers. The plane is traveling horizontally at 40 meters per second at a height of 100 meters above the ground. Okay, so we know we've got the vertical motion of the aircraft at 40 meters per second, so that's its velocity. And of course, you can see by the notation, we've got V naught equal to 40 meters per second because that's where we're starting the problem. These are kind of like called boundary value problems. The boundary is the starting point, and we know that the aircraft is at an elevation of 100 meters. Okay, so we know that in our problem, the initial velocity and the vector velocity, or the velocity in the x direction, in the horizontal direction, is the same, 40 meters per second. So the first part of the problem asks, where does the package strike the ground relative to the point at which it was released? So at some point back here, they're going to have to dump the package out so that its velocity is going to carry the package to the stranded hikers. And then we're going to calculate what are the horizontal and vertical components of the velocity of the package just before it hits the ground. So let's first find the range of the package. We need to first calculate the time of flight. So in this case, we're going to use our relationship that the change in the y direction, y final minus y initial, and let's use the relationship v naught in the y direction times time minus 1/2 times gravity times time squared. Okay, so when we do this, we calculate the range x sub f. So we have y equal to minus 100 meters, okay? And in doing so, setting it negative, then we have minus 1/2 and the gravity 9.8 meters per second squared times time squared, okay? So we know that we have from y final minus y initial minus 100 meters, okay? And because we're using the acceleration of gravity, it's a free fall in the y direction. Okay, you have to remember, you got to keep track of which axis. We're looking at the free fall in the y direction. There's our negative sign already in place. So the relationship says 1/2 gravity times time squared. Okay, so we're going to multiply through both sides times 2. So that gets rid of the 1/2. So we have 2 times 100 meters equals 9.8 meters per second squared times squared. You'll notice that negative sign cancels each other out, so we've got a positive problem going on here. Okay, so now we have numbers and everything else except time. Okay, so we're going to solve for time. Okay, so in doing this, we're going to move 9.8 meters per second squared to the other side of the equation. So now we have 200 meters, 2 times 100, divided by 9.8 meters per second squared. And when I take the square root of both sides, the square root of t squared gives me t, and I divide 9.8 into 200 meters, I get a value. I take the square root of that value, I get 4.52 seconds. So that is the time of flight. That's the time of flight of the package flying through the air to the stranded hikers. Now I want to calculate, knowing that time of flight, okay, and I needed that time of flight, I need to calculate what the distance is, because that's what the problem asked for. Find the range of the package. So the change in x, then, x final minus x initial, I can use the relationship that delta x is equal to v naught in the x direction times time. Okay, so we know that of our terms here, x sub I is 0, so that cancels out. So all I have left is x sub f, is where the package is going to land, is equal to v naught x times time. So 40 meters per second we know is the velocity in the x direction that the package is moving, at the same velocity as the aircraft, and times the time of flight, 4.52 seconds. So we get a downward range then of 188 meters. So it takes 4.5 seconds for that package to leave the aircraft and fly through the air downrange 188 meters. Okay, that's part A. Part B asks us then to find the components of the package's velocity, v sub x and v sub y. Okay, so we're looking at, remember those two vectors that we saw in the diagram on the parabola. So we got the x component, and the y component. So v sub x we saw was velocity initial times the cosine of theta. So in this case, 40 meters per second is the initial velocity times the cosine of 0. Why 0? Because that's right along the x-axis. That's the direction that the package is moving. So when we take the cosine of 0, which gives us 1, we end up with 40 meters per second. So that's the x component. The y component for the velocity. Vy is equal to v naught sine theta. Now we have to include gravity. So v naught sine theta minus gravity times time. Notice there was no acceleration in the x component, but in the y component we've got a component of gravity in there. So 40 meters, okay, times the sine again of 0. That's the angle that it makes. Minus 9.8 meters per second squared times the time of flight, and we get then a velocity in the y direction of minus 44.3 meters per second. And it would make sense that the velocity in the y direction would be a little more. Why? Because we've got gravity pulling it down, accelerating the package in the y direction. There's no acceleration in the x direction. So 40 meters, 44.3 meters. Okay. So if we look at observations then made in different frames of reference, can be related to one another through the techniques of the transformation of relative velocities. If we look at this problem, we've got a boat. The boat is heading due north as it crosses a wide river with a velocity of 10 kilometers per hour relative to the water. Okay, the river has a uniform velocity of 5 kilometers per hour due east. Okay, determine the velocity of the boat with respect to an observer on the riverbank. So we know that the river is moving at 10 kilometers per hour. We know that, or 5 kilometers per hour. We know that the boat is moving at 10. So what we need to do is break this up into its components so we can determine then each of our relative velocities, okay? So we've got 3 components here for our relative velocities, okay? For the boat and for the flow of the river, okay? So if we look at this component-wise, the vector, boat, river, x component, there's no velocity. But in the y direction, we know the boat is trying to go across the river at 10 kilometers per hour. So we only have a y component. Okay, the velocity of the boat from the boat and this should be the observer. Okay, heading due north. Okay, so VBE. Notice that we've got 2 unknowns that we're solving for. We're looking at the component of the velocity in the x direction, the component of the velocity in the y direction. And then the river itself, the velocity for the river is 5 kilometers per hour and no x and no y component. So we've only got a y and an x component for the boat and for the river. So how do we calculate these component values? So if we use our relationships here of 0 is equal to the velocity in the x direction minus 5 kilometers. Okay, so what we're calculating here is the river component. So velocity x then is equal to 5 kilometers per hour. That makes sense because that's the moving water. Now we calculate the boat in the y direction. So 10 kilometers per hour is equal to the velocity in the y direction minus 0, okay? Because we end up with an initial velocity there, okay? So the y component is 10 kilometers per hour. So now what we have to do is use our Pythagorean theorem, because what we need to do from the diagram here, you can see the vector v sub br, the vector v sub re, and then we have our vector v sub be. That's actually what the boat is going to do as it's trying to go across, and the river is moving it down, so you end up with that hypotenuse. So we stick it back into the Pythagorean theorem. V sub be becomes the resultant. So that's our x component, our y component. So the river, 5 kilometers per hour squared. The boat speed, 10 kilometers per hour squared. We end up with a velocity of 11.2 kilometers per hour as the boat is being pushed along the river. To calculate the angle, the inverse tangent of the components x and y, okay, so we end up with 5 divided by 10, inverse 10, gives us an angle then of 26.6 degrees. So our entire solution, VBE, looks like 11.2 kilometers per hour at an angle of 26.6. Okay, so we've looked at scalars, vectors, properties of vectors, components, velocity, acceleration, projectile motion, and in the last section, the relative velocity. Okay, so when we come back, section 4, we'll start looking at forces.